easy this is to modify your air conditioners?
Yeah, it's a really simple at-home project.
Yeah.
I just say playing these games.
They would make the prisoners dig the hole too, though.
Yeah, right. Were we saving this rock for some reason?
Yeah. Goes on top.
It's often the light. Come on, maybe at the bullseye. Laid you out.
Hi. About a year ago, we did a video where we demonstrated the remarkable multiplier effect in heating a room using a heat pump or an air conditioner, as opposed to a typical resistance heater like a space heater. Even though the space heater is 100% efficient at converting electrical energy into thermal energy, nevertheless, the heat pump is several times more efficient than that. Now, that might seem impossible, but as you'll come to understand, it is not. At the end of that video, I teased the audience saying that we were working on a method to further enhance the performance of air conditioners. That's what we're going to do today. I'm going to demonstrate this, I'm going to show you how to do it, and it's easy. To begin with, it would be helpful to have a little bit of background in some thermodynamics. And don't get nervous because I'm going to keep this short and to the point. Firstly, what is heat? What is thermal energy? The fact is, it is the sum total of all of the kinetic energy of the particles in a material, whether it's the air molecules bouncing around in here or the carbon atoms vibrating in a diamond. When you add up all of the kinetic energy of those particles, you have the heat energy. According to the formula, 1/2 mass times velocity squared, 1/2 mv squared. So when you add heat to a system, you obviously are not increasing the mass of the particles, you must be increasing the velocity. As you continue to add heat, the velocity can be so great that solids fall apart, they melt. Keep adding additional heat, and the liquid is no longer stable, and it vaporizes into a gas. The other principle we have to cover is one that can actually confound a lot of physics students and even a few professors. It's related to that dirty word, entropy. Now, entropy has a lot of subtle implications, but for our purposes here, we can pretty much just substitute the phrase, the tendency toward equilibrium. The fact that when you have a system with different energy levels in it, they tend toward an average as opposed to diverging to higher and higher differences between the energy. Entropy is that tendency toward averaging. For example, if you have a mountain with all the rocks and boulders and soil piled way above the surrounding terrain, you have a lot of potential energy in that system. And because of entropy, given enough time, hundreds of millions of years, that mountain will eventually erode down to the surrounding terrain level to be at the exact same distance from the center of the Earth. Entropy always wins. Now, if you decided to climb that mountain before it erodes down to the Earth, and you reach the top and you decided to celebrate, you're going to build a little cairn, little stone structure. So you go around the peak, you find the rocks, you put them together in a little structure, takes you an hour, congratulations. If you decided to do that same process of construction, but you were at the foot of the mountain, same structure, same size rocks, you'd use the same amount of energy. Because you really haven't affected the energy or the potential energy of the system, you haven't opposed entropy. But if you had to climb all the way down the mountain to bring those rocks up to the top, you probably would never get it done. It would require a tremendous amount of energy to do that, to oppose the entropy. As an interesting thing, even though you are effectively lowering local entropy, again, entropy always wins. Global entropy does. So the sun has to hit the farm, they have to grow the plants, they have to bring it into the store, you have to buy it and cook it up into food to power the engines that carried the rock up to the top. But we're not trying to cool the universe. We're trying to locally reduce the temperature. And so we can afford to affect entropy locally as opposed to being concerned about the global effects. Now, you might wonder what the heck entropy has to do and what the nature of heat has to do with the air conditioning. But it's actually related to the first thing that I talked about, which is, remember that the heat energy is related to the velocity of the particles. That system starts at absolute zero, 0 Kelvin or minus 273 degrees centigrade. That's very cold. So when you have nicely air-conditioned air in your room at, say, 20 degrees Celsius, it contains 95% of the thermal energy of the hot air outside of your building. It's just 5% difference. It's a very small difference in a very large number. And this is why a heat pump can have such a high multiplier effect, because most of the hot air that comes out of the air conditioner comes from the air inside of the room. It's actually stealing most of that energy, raising it up 15 degrees to be able to dump it outside, while the space heater has to directly convert electrical energy into that kinetic energy, into the velocity of the particles. That's why these things can be so efficient. But it also suggests that if you want the air conditioner to work even more effectively, you need to work on that remaining 5% differential. Bottom line is, the most efficient time to use an air conditioner is when you don't need it, but it's obviously not the practical time to use it. This is the secret or the principle behind the advantage of geothermal air conditioning. Because just a half a meter below the surface of the Earth, the ground temperatures are remarkably cooler in the summer and warmer in the winter. We're talking about 11 or 12 degrees Celsius. Go down another meter and it's maybe 13 degrees colder. Go down another 5 or 10 meters, 14 degrees colder. The rate of decrease slows as you go deeper, but it continues for a long time. Now, some of you may be saying, oh, okay, he's just talking about geothermal air conditioning. This has been around for a very long time. As a matter of fact, you can even go out and purchase a commercial unit. You can. And about 2 years ago, we had a contractor come out to our home to look at redoing the air conditioner for our home. And we needed a 6-ton system, which is 70,000 BTU. And the quote came in at just a hair over $20,000. Most of that money is required to dig the holes or the heat sink that's effectively going to take the heat from the air conditioner and get it into the ground. So as you can imagine, if you've been following this channel and just the background you see, we do a lot of research. We deep dive, and that's what I did with this air conditioning system. So when they came back, I asked a question. I said, you say that I need 4 of these boreholes, each 80 meters deep. What if I was a multimillionaire and I just said, I don't care, you want 4, what if you put in 8 boreholes? Would I enhance the efficiency? And the answer was yes, by a couple of percent. So then I thought, what if you invert this and we just used 2 boreholes? Would I lose efficiency? Yes, 4 or 5%. All right. What if we go down to 1 borehole? Well, then it may become 40 or 50% less efficient. What if we used only a 40-meter borehole instead of the full 80-meter? Then the efficiency may drop by 4 or 5-fold, 400 or 500%. It isn't linear. And it kind of makes sense because when you think about it, what comes out of the air conditioner, the fluid that we're going to be dumping the heat into the ground with, is at its highest temperature as it exits the air conditioner. As that hot fluid is traveling through the ground, it transfers its heat into the ground. And at that point, when it first enters the ground, it has the highest heat differential, the highest heat transfer. As it loses its heat and cools down closer and closer to the temperature of the surrounding soil, the heat transfer continues to slow. It never stops, but it asymptotically approaches 0. So what we're going to do with this test is we're going to combine the fact that we're using a smaller air conditioning system. These are half-ton units at 5,000 BTU. And we're going to cut corners on the geothermal ground loop. And when you multiply both of those factors together, you make the holes that you have to dig so much smaller that you can do it yourself. You can hire somebody for about $200 to bore a hole for you, or if you've got a buddy and you can call in a favor and you've got enough beer, the two of you could probably get it dug in about 2.5 hours. Now, some of you are probably thinking, oh, this is sounding kind of intriguing. I'm getting interested. Others may say, yeah, but does it still work? Yeah, it really does. So let me kind of cover how we're practically going to do this test. In order to do a comparison, I bought 2 identical air conditioners at the same time. And one of them, except for removing the case to show the internals, is completely unmodified. It's our control. The other unit requires some modification for the geothermal system, but again, it's not complicated. It doesn't involve any electronics, no plumbing, no HVAC work. It really only requires modest level carpentry skills, as I'll explain in just a sec. Now, to understand why we're doing it this way, it might be a little helpful just to review what's going on in the air conditioner itself. Except for some unusual systems, like when we built our solid-state refrigerator and freezer systems based on Peltier devices, all air conditioners use a circulating fluid. In the distant past, they use fluids like ethane or propane or carbon dioxide. Some of them even used water vapor. And probably the most successful long-lasting agent or fluid was ammonia. But nowadays, it's limited to a couple different formulations of a chlorofluorohydrocarbon. And rather than getting into the details, because we're not going to disassemble this or have to fill anything, let's just call it Freon because it's easier to say. What happens in a typical air conditioning system is that you flow into the compressor here a relatively cool and relatively low pressure Freon vapor. The compressor squeezes it down to about 15 atmospheres of pressure where it gets very hot. Because it's so hot, it still remains a vapor as it exits the compressor and goes back into the condenser where it condenses. As the heat is released into the outside air, it begins to form a liquid. The pressure really doesn't drop because we're constantly flowing behind it more hot, high pressure vapor. What exits the condenser is a relatively cool, high pressure liquid Freon that comes up through this tube. That's why it's a smaller diameter. This tube goes all the way to the front of the air conditioner where there's an almost identical coil called the evaporator. Inside of there, that liquid evaporates, it boils, and when it does so, it gets very, very cold. The room air, as it circulates through, dumps its heat into that very cold vapor. And so what exits the evaporator is a relatively low pressure, relatively cool Freon vapor, which then returns to the compressor and the cycle continues indefinitely. So obviously the modification we need to make is in the condenser, how we're going to dump the heat out of the system. And to do so, what we need to do is better access the condenser coil. So the first step was to remove this plastic shroud that surrounds the fan that guides the air through the condenser. Once I had exposure of that, I then saw the full condenser fan on the back, and because we're not going to be using the fan, I removed it. I simply took a hacksaw and cut it off. Now, the motor that powers this condenser actually has 2 shafts coming out of it. The back shaft attaches to the condenser fan, and the front shaft attaches to the blower for the inside air movement for the air conditioner. The fact that we're removing this fan is actually very significant later on. You'll understand why. Now, in order to cool off the condenser, now that we've exposed the coils, I built a box in order to be able to flow liquid through it. The material that I'm using for the box is this PVC foam board that I've used in probably 24 projects. I really like this stuff because it's widely available, it's relatively inexpensive, it's lightweight, it's homogeneous because it doesn't have any grain structure or voids. It's not bowed, it's a pretty precise slab of material that you can easily work with. It's also impervious to water. It is a great thermal insulator, a great electrical insulator. It takes glue very well. As you can see, this little glue line here, I think I did a pretty good job. And it's easy to machine. So it makes it very easy to work with. I also think it looks pretty nice. So what I did is I measured the size of the condenser coil, and one thing that I should have mentioned earlier on, I surreptitiously examined a few other models in the store to make sure that the input and output lines from the condenser coil came from the same end. It's not a deal killer, but it certainly makes the construction of this box a lot easier, because I effectively built the box with 5 complete sides and about 1 centimeter of clearance around all of the different parts so that it would safely get on and I'm not going to be struggling. In addition, it needs to be made long enough so that it not only slides over the coil, but also slides over all the fiddly bits that are sticking out here that you have to seal up. This would be very difficult to do in a hard component. And so to seal it up, I used typical bathroom 1-part RTV silicone sealant. This stuff is kind of neat because obviously it's inexpensive and easy to get, but it has an unusual feature, and that is that it cures by exposure to humidity in the surrounding air. So if you're going to do your bathtub and you put down a little 3mm bead, in about 4 or 5 hours, it's cured and you can use it. But if you just double the diameter of the bead to maybe 6 or 7 millimeters, it might take a full day for it to cure. Go to 1 centimeter and it might take a week. And so we want a very thick layer of this material because it's not only working to seal the end of the box, but it also, because it's very thick, locks in all of the internal structure, providing some support for the condenser coil so it's not just dangling on its tubes. The trick is you don't put it on in one big thick layer, which might take a month to cure. It will stick to previously cured layers. So in the morning, you go out with your little gun and you cover all the metallic surfaces that you can find, but with a thin layer. You'll smell the acetic acid or the sort of vinegary smell when this stuff is curing. When you come back later in the day, that smell should have pretty much dissipated and you're ready to put on a second coat. The next morning, a third, and the next evening, a fourth, and you're pretty much done. It's going to be cured in about 2 days instead of a month. Once I did that, I needed to test it to make sure that it didn't leak. And so one feature about this box is that there's an output and there's an input lead or port that's been drilled into the side of the material, tapped, and then a little hose barb was just screwed into the top of it. So I plugged the one port and then I attached to the other port a funnel with a tube and filled the entire thing with water up to about here and looked for leakage. I had some. I had a little pesky drip that just kept coming out. And I was kind of surprised because I thought I did a really good job. But nevertheless, it's always good to test. So once I discovered that, I then drained the system, put on 2 more layers of this, retested it. It's perfect. Everything worked just fine. The only other thing you'll notice here are these little metal clips. We don't want to depend only on support at the bottom of the box as we're moving this thing around or wind is hitting it. And so these clips just provide some additional rigidity to the structure and just go into the solid material on the side. And the fact that it machines so easily makes it really easy to put those things on. You can see just one of the many probes that we're going to be having operate during the actual demonstration of the unit when we instrument everything up. But we're pretty much done in here. So we're going to take a break. I'm going to move both of these air conditioners into their respective windows, and then we're going to start some of the testing. See you in just a bit. Okay, so we've set up the air conditioners for the comparative test. And obviously I've instrumented the heck out of this. I'd have kept going, but I ran out of vices. But to break this down so it's a little bit easier to see what we're looking at here, let's start with this meter over here. This is a temperature meter that has two probes attached to it. One is just taped to the inside of the room to give us an indoor air temperature. And the other probe extends outside the building and away from the wall of the building to give us an outside air temperature. This is basically giving us the environmental conditions for the test, and we'll occasionally refer back to this meter. Now you can see the two air conditioners have been put in the window. This is the control unit that's been not modified, and this is the geothermal unit over here. Each air conditioner is plugged into a power meter that will measure the amount of power consumed during the test. One thing you'll notice is that this particular power meter has two plugs in it. When you have a geothermal unit, you need water circulation. So we have a small aquarium pump over here that's doing that duty. But because we want to be fair in terms of the energy consumption, we have to include it in the energy budget of the geothermal unit. In addition to that, we also have two additional temperature meters that we'll get to in just a little bit. We also have an air velocity meter, or an anemometer. This measures the air velocity coming out of the cold side of the air conditioner. And because these systems are identical, both in their dimensions as well as their design, when we measure the airflow velocity coming from each of these at exactly the same location, we're really comparing velocity at the same time we're comparing volume, the amount of air that's moved through the air conditioners. Now we're not quantifying it. We're not saying it's 3 cubic inches per second or 4 cubic meters per second, but it's a relative measurement of the amount of air that's moving through the two systems, which is pretty important. Then we also have my phone mounted up here that's going to be operated as a decibel meter to measure sound level during the test. Now, before we move to the outside to show you all the plumbing, I thought it might be kind of interesting to start some of our testing and get it out of the way. So I'm going to turn on the control unit here, turn its fan onto high speed, and its mode to cool. Now, these air conditioner units have a boot up period while they're sort of getting everything organized in their little brains. At the same time, certain components are warming up and certain components are cooling down. And so we're going to give this 10 full minutes to reach a steady state, and then we're going to take some readings from this particular unit. So I'll see you in a sec. Okay, so it's been 10 minutes. And you can see that the power consumption on this unit is 420 watts. I've got the anemometer set up here. Okay, exactly right. And I'm presuming you can see this. There's a little bit of turbulence, so it kind of goes up and down. But we'll call it 1.8 meters per second. 420 watts, 1.8 meters per second. Then call it 61 decibels. Okay. 420, 1.8, 61 decibels. Let's turn this unit off, and let's go ahead and turn on the geothermal system. Fan to high and mode to cool. Okay, we're going to give this unit 10 minutes in order to reach equilibrium. See you in a sec. All right, 10 minutes. So let's take a look at the power consumption. 378 watts. So this thing is using about 50 less watts than this unit is, despite the fact that we are also powering the aquarium pump. The reason for that is this old condenser fan. When we removed this from the blower motor that powers the inside blower and the outside blower, we reduced the drag on that motor tremendously, and as a result, it uses so much less power that even though we are adding the water pump to the system, to the energy budget on this unit, we're still using about 50 less watts, which is pretty significant. In addition, let me just be real accurate here. I'm just going to check something once more. Yeah. That's perfect. Let's take a look at airflow velocity. Now again, there's a little turbulence, but I would put this at about 4.05 meters per second. 1.8 to 4.05. That's 2.5 times the airflow. How's that possible? It's this guy again. Because we removed this drag from that motor is turning now substantially faster, and it's moving 2.5 times more air through the room because it's unloaded. That's going to be very significant. Now let's take this guy out of the way and see what that extra airflow does to sound level. "51 decibels. That's 10 decibels lower than this unit here. Sound decibel readings, decibels are a logarithmic scale. So if you reduce the sound level in this air conditioner by 10 decibels, you've reduced the sound pressure by an order of magnitude, tenfold. This is 10 times quieter, and it's noticeable. When you turn this thing on, it sounds like a window air conditioner. When you turn this on, it sounds like a window fan or a central air conditioner. It's substantially quieter, which is pretty neat. And again, it's because of this guy. This generates most of the noise associated with the air conditioner. So we went from 420 watts to about 380 watts. We ended up increasing the airflow from 1.8 meters per second to about 4.1 meters per second. And we've reduced the noise level 10 times. This is pretty impressive. Now, before I do the temperature measurements here, I want to be fair. And the problem is we had this unit on for a while, then we turned it off, then we turned this unit on, we would leave it on. That's not a fair measurement. So I'm going to turn off both units, and we're going to let them sit for about a half hour to reach a baseline temperature. And then we're going to test them simultaneously to measure the temperature output from both units. So we'll see you in a little bit. Meanwhile, it might be kind of interesting to go outside and take a look at some of the plumbing and what we did outside. So let's head out there while we're waiting for this to happen. Okay, so we're outside. This is the setup out here. We have the control unit over on the left. We have the geothermal unit, obviously, over on the right. One thing that you can see is that I have this thermal probe jammed into the condenser box to give us a rough estimate for the output temperature of the air flowing through the condenser and a rough estimate of the freon temperature inside of the system. Over here, you can see that we have the output tubing that runs from here into the house or into the building, is pumped then down into the ground, and then it returns from the ground to the input tubing over here to fill up the box and continue the cycle. You'll also notice the two temperature gauges that we've got mounted in here, measuring the output temperature from the condenser box as heat is added by the air conditioner, and the input temperature from the ground, measuring basically the ground water temperature. We're going to see a small differential occur as we use this, but this is the reference that we're using for temperature. The other thing you'll notice is these bulky valves that I placed here. This was done to fill and to purge the air from the system as I put the water in originally. Now, it turns out that I expected I would get a lot of bubbles coming up over time with the de-dissolving of gas and vapors, but I didn't. It really was, you just filled it, opened that up, closed it, and it's been fine for weeks. So as a result, I don't think you need this bulky valve. I had them, and so they were free. But if you were going to be doing this for a permanent installation, I'd just get some watertight screw caps to put on there so that you could fill and empty this at the beginning and end of a season. It's going to be more aesthetically pleasing, it's going to be less expensive, and it's going to be more compact. The other thing that you'll notice is that we have 4 PEX lines going into the ground, even though we have 2, a feed and a return line. The reason for that is that when I originally did the test with the water pump in a basin just to determine its output, it flowed 1.2 meters per second, which is excellent. 1.2 liters per second, which is excellent. However, when I ran that pump through 300 feet or 100 meters of the PEX tubing, the flow rate dropped to 65 milliliters per second, which wasn't too good. So I cut the tubing in half. So I had 2 50-meter segments. And then I flowed the water through one of the segments, and I got 130 milliliters per second. So we're actually running the 2 50-meter lines in parallel, which doubles the output again to 260 milliliters per second, which is excellent. And that's why you see the 4 connections down here and the 2 feed lines. Over here, interesting story, this is the probe that measures the outdoor air temperatures during the test. And the interesting story is that when I was setting this thing up, our UPS driver stopped by. And as you can imagine with this channel, we get a lot of UPS deliveries. And she follows the channel and is actually a subscriber. And when she stopped, she said, "Oh, what are you up to?" And I said, "Oh, we're doing a video on geothermal air conditioning. And I'm just mounting this little temperature probe off here like this to measure outdoor air temperature." And she stared at it for a few seconds and she said, "Isn't that going to give you a false reading because it's in the bright sunlight?" And I was kind of like, yeah, you're right. And it was an easy fix. I just drilled a little hole and put it down here so that it's in the shade, and it solved the problem. But it had a profound effect on me because here you've got a UPS driver, you've got coworkers, you've got people that you pass in the street every day, and you don't realize the amount of cumulative wisdom, knowledge, experience that these people possess. And so this is one of the reasons why I'm so enthusiastic about the future of humanity. Finally, this hole was a bit of a challenge to construct, but it was a lot of fun, and we're going to show you that next. Okay, so basically what Dan and I are going to do is we're going to be putting this PEX tubing down in the tube in the hole. And what I found is that the water pump that we use to flow the water through the PEX tubing went from like a liter per second or a quart per second all the way down to like 60 milliliters per second, like a 20-fold drop.
Yeah.
So when I cut the tube in half, this is actually 100 meters or 300 feet. Now it's 2 150-foot coils. The flow doubles because you got half as much tubing.
Right.
But then we run both tubes at the same time, so we double it again.
Yeah.
So that is plenty of water flow, and so what we're going to end up having to do is put this tubing down in the hole and have coming up out of the hole about a foot of the ends that I have just plugged on to clean, so we can connect it up to the thing. The filling operation is, this is basically how it's going to go, is that you're going to fill up one of these buckets that I've already marked with water to this level here. Then, with the scale that we're going to have out there, you're going to add about 23 pounds of sand. So I've got scoopers and a bucket and everything like that. You're just going to add the sand in there with minimal rocks, that kind of thing. And then you can see where I was doing some of it over here. That is how we're going to fill this thing with sand and water. That's kind of your job. Then then you'll sort of deliver that to me. And then I'm going to come over here. I'm going to put the bentonite and the graphite in there, put it in the mixer, and and mix it up for about a minute. Once it's all blended, then I put a bucket out there. You dump it in the hole, and maybe with a scooper, or maybe with your hand, I don't know. But get like 90% of the shit out of the bottom. And then once you fill that up, you fill it up with water again, and we start the whole process. My estimate is probably about 40 buckets are going to be needed.
That's pretty good.
Yeah, right. And the other thing is, once we get to about a foot from the top, we don't really need thermal conductivity anymore. So we can just backfill it with the sand, you know, so we don't have this black look on the driveway. And also it just saves time and effort and everything like that. Yeah, now this, because it's been sitting here since my testing for about 4 days, is thicker than it actually is. I want to use these samples that I made for the testing. They're surprisingly heavy. You know, you get a feel for one of these things. It's like, it weighs. But the point is, this stuff, when we pour it into the hole, is going to get a lot easier after these first 4.
Oh, yeah, no.
That may end up being the best. I've never done this before, and that hex is really rough to work with.
And just let me know if you need me to get out of the way or anything.
Sure. What are your thoughts?
Oh. So you need both of these sticking out. You need,
Yeah.
like,
That's kind of why I was thinking doing it from the middle, but it may end up being
yeah,
that
that's
that's...
what I mean. Run it out all the way to the middle and put that in there.
Yeah.
Well, I'm recording right now, so it doesn't really matter. It gets up until the, just so you know in the future, it gets up until the edge of the barn.
Okay.
That's what it gets, so.
And it doesn't have to be perfect. Like if one side ends up 2 feet too long, I'll just cut it off.
Yeah, yeah.
Careful of it, yeah. That's gonna be fun.
Should we twist them up?
Yeah, I'm trying to untwist them. It'd be better to have them loose because they do need to sort of be uncoiled in the hole.
Okay.
What do you think? Is it going to work?
Yeah, we're gonna like adjust it though a little bit. Probably with something.
See those boards inside the garage? Would those push it down nice?
Cause you want it to be like pretty much all the way in the bottom of the hole, right?
The deeper it is, the better it'll work. I'm not accomplishing much. Would my hands help?
Sure. Yeah, weird.
Not bad. This isn't a precision operation. We just don't want to kink it.
Yeah.
Okay, so it's actually been a little closer to 40 minutes. So I'm going to get some of this equipment that we're not going to need out of the way here. We've already established that. And this. Now I'm going to turn on both units at the same time. Power, power, fan to high, mode to cool, fan to high, mode to cool. Now we're going to give these two units again 10 minutes to reach equilibrium, and then we're going to take some temperature measurements primarily with this and with this. Okay. All right, see you in a bit. All right, while we're waiting for the systems to all settle down to do the final test, I want to cover the two major takeaways from this video. The first one involves the condenser fan, as I explained. By removing this, we decrease the power that the system uses, we have increased its efficiency, and we've made it substantially quieter. So it's a win-win-win. The other takeaway is this: mud. You see, when drilling is done, whether it's oil well drilling, water well drilling, or geothermal borehole drilling, they will typically use a material called drilling mud to help in the process. You see, when you place a drill into the ground and you begin boring down, there's a lot of friction with the surrounding soil, and this eats away at some of the available horsepower for the drilling operation. A drilling mud usually consists of a combination of water, some bentonite, and a few additives that makes this thick, very slimy liquid. And what this does is, because it's so slippery, it acts as a lubricant to reduce the drag of the drill as it's doing its job, so that more of the horsepower that's available is actually powering the drill bit to send it down through the ground. In addition, drilling creates a lot of heat, and so the high water content of this mud helps to cool the components, increasing their longevity. And finally, you produce a lot of debris, sand, dust, grit, that you need to get out of the hole. And the bentonite acts as a wonderful suspension medium to allow you to pump this material out of the hole and make room as you continue to bore down deeper and deeper. Now, in geothermal applications, they also use a compound called mud, a geothermal mud or a geothermal grout. It's kind of similar to the drilling mud, but it's for a completely different purpose. You see, when we pump the water down through the system and into the PEX tubing, it's an excellent conductor of heat. It brings the heat underground. And even though the tubing itself, the PEX tubing, has a relatively low thermal conductivity, the walls are very thin. So the heat is pretty easily able to exit and get to the outer surfaces of the tube, where it reaches a roadblock. You see, typical soil has very low thermal conductivity. It's not just because of the silica and the minerals that are present, but there's also voids, there's air gaps, there's organic material, and it's a lousy thermal conductor. So what the geothermal mud is intended to do is act as a thermal interface, kind of like the grease that you use when you're installing a CPU in a computer. It helps to get the heat from the tubing into the surrounding medium. So typically what you would do is, once the hole has been bored, you'll put your tubing down and then you will backfill it with the geothermal mud to act as this thermal conductor. Now, the typical mixture for a geothermal mud is 40% sand, 10% bentonite, and the remaining equal amount, 50%, water. And this produces this sort of thick, creamy mess that has about twice the thermal conductivity of the surrounding soil. So it's a good interface material. More than 90% of all geothermal installations will backfill with this material in order to fill up the boreholes and provide that conductivity. But there's been some recent advances in this material, and we've taken advantage of that. Probably the most promising is the addition of graphite. Graphite is a remarkable material. It has a tremendous thermal conductivity. It approaches that of diamond. It's higher than almost any metal out there. Actually, it's higher than all metals. And so by adding just 3% of the dry weight, in other words, replace the sand with 3% graphite, will double the thermal conductivity of the material. But in addition, graphite is a wonderful lubricant. I use it in the shop. A lot of people use it in machining because it's slippery. And so the addition of that graphite actually lowers the viscosity of the material. These two basins contain exactly the same amount of solids and water, but you can see that the typical geothermal mud is far thicker, much more viscous than the mud that has a few percent of graphite placed in it. This makes it easier to pump down the holes, and when you're surrounding the tube, less likely to have air gaps or bubbles around it. It's a really good advantage, plus it doubles the thermal conductivity. But we can go further. You see, the graphite has excellent thermal conductivity across each one of the particles. But when you're using a relatively low percentage, these particles are isolated from each other by the sand, the bentonite, and the water. And so it can help the thermal conductivity, but it's somewhat stymied by the surrounding material. Graphite, however, is available in a variety of different forms. You can get graphite that is as fine as dust, all the way up to large flakes that are almost the size of cornflakes. And so if you use a flake style of graphite instead of the powder, some of those graphite surfaces, those plates or those surfaces, the flakes, can actually touch or be very close to each other and bridge the thermal gaps, allowing the heat to transfer much more quickly. The result is that if you use 3% graphite flakes instead of powder, you can double the thermal conductivity again. In other words, quadruple it. That's great. One problem is if you keep pushing the graphite flakes, they become thicker and more difficult to be able to pump and to flow. It doesn't work as well as a lubricant as the powdered graphite. So what we did is something that I haven't seen in research papers. I don't know if anybody has looked at this, possibly, but I haven't seen any reports. And that is the concept of mixing two different forms of graphite. We did this when we were experimenting with ultra-high performance concrete and with the barium sulfate that we used in our ultra-high performance or ultra-high reflectivity paint. When you have vastly different sized particles, they can work synergistically, they can lock together, they can couple more efficiently. And what I found is that by adding 3% graphite flakes and 3% graphite powder, the end result had a little better thermal conductivity than the original just with the powder. But it also retained the very low viscosity, which makes it easy to work with. Now this would be a great addition if you were doing typical geothermal work, because it flows better, it has higher thermal conductivity. But for our applications, it may have an even better or additional benefit. That's because a typical geothermal well is very small in diameter. It's about 5 inches or 12 centimeters in diameter and as much as 100 meters deep. So you can imagine as you're drilling down, this thing can easily collapse. You try to get your tubes down there, they can get crushed and jammed up. And so you will either need to compress the walls by some application of some pressure, or you need to use some sort of a geothermal cement or concrete in order to form a stable wall so that you can put your tubes down there and then backfill with the liquid. But in our application, where we're hand digging or using an auger, the surfaces, the outer surfaces of the hole are very messed up. They've got voids, they've got irregularities, rocks missing. And the result is that with this very low viscosity material, it can infiltrate a little bit into the walls of the hole, greatly improving the interface with the low thermal conductivity surrounding soil, improving this even better. And so I think it's the combination of the reduction of drag and the improvement in the geothermal mix that explains the incredible results that I'm going to show you now. Okay, so we've given them 10 minutes. So let's turn on the temperature probes here. Make sure you can see them. And let's see what we've got. Power-wise, 432 watts. Power-wise, 400 watts. So there's still a significant difference, but the power has gone up in both as they've continued to cool. Now here's the interesting thing you'll see. This probe here which is in the outflow from the cold side of the air conditioner, is going in here. This is at 14.7 degrees Celsius. Similarly, we have a probe over here that is going in. That is the yellow probe, and we can see it's at 14.2 degrees. So they're very close. Even though this is a little bit cooler, they're very close. Here's the interesting thing though. Remember, even though we're using less power, even though this is a little bit cooler and it's quieter, this unit is flowing 2.5 times more air through it and cooling it off more than this unit over here. This thing is effectively working about 2.5 to 3 times as efficiently as the stock unit. Oh, and it's quieter as well. Now, this is really fascinating because remember what I said at the beginning of the video about heat pumps. They effectively take the heat energy out of this room. They have to boost it up. They have to pump it uphill in order to be able to dump it outside. The fact that this unit here has an outside condenser temperature of 42 degrees, this thing is having to elevate the heat about 28 to 30 degrees in order to dump it outside. This unit here, if you look at these top two measurements, 30 degrees and 27, the average is about 28. This only has to elevate the temperature about 14 degrees. So effectively, this unit is working half as hard, and that explains a lot of the efficiency gains that we see in this particular unit, in addition to the lack of the condenser fan. This is a huge finding because when we do videos, a lot of the videos we do, Alex and I will discuss a topic, decide what we want to cover, what's interesting. Then we build it, we test it, and we say, okay, this is going to make a video. We produce the video in order to share what we've learned as well as our excitement about the discovery. Some of the videos we do are so successful that we keep the units. I'm leaving this thing in here permanently. This thing is so good and so efficient. We're going to keep this air conditioner here basically forever. In addition to that, one of the things that you have to take into account is cost. When I purchased these two units, I bought them from Home Depot and they cost me $159 each. This unit though has additional expense associated with it. We have a water pump down here that costs $40. We have the flexible tubing, the tie wraps, the fittings, all of the other fiddly bits that make this system work. That cost $60. We have the PEX tubing in the ground. That's $100. We needed $120 of bentonite, $70 of graphite. In addition to that, we decided to have our hole bored by a professional with an auger to save ourselves some effort. That cost $150. The end result is when you add all of that together, this system cost $700 while this system cost $160. And you might think, but remember, this thing is cooling 2.5 to 3 times as more effectively as this unit here. This is really comparable to a 12,000 to 15,000 BTU unit, which will typically cost you about $550 to $600. We're in the ballpark. But the real effect is the cost savings in terms of power. That 12,000 to 15,000 BTU unit is going to use about 1,200 watts continuously. This unit is using 400 watts. You save 800 watts using this system. Now here in New England, electricity costs about 23 cents per kilowatt hour. So effectively, we're saving about 20 cents per hour using this system as opposed to a much larger commercial system. That's $4.80 per day, or $150 per month. This is a significant savings in terms of power. In addition, if you don't just plug into the grid, but you're off-grid, or you have alternative energy systems like solar power and batteries, the fact that you're using so little power gives you a lot more flexibility. You may not have to upgrade your system in order to be able to handle these much larger air conditioners. Now, for those of you that are familiar with geothermal systems and you say, this kind of like tripling the efficiency, this is unheard of. Well, remember, typical air conditioning systems that are being used for geothermal installations, like the kind that we had quoted for us, are based on a comparison between highly optimized, large power consuming air-cooled units and geothermal units, which typically show an improvement of efficiency of about 60%. But when you get to window air conditioners that are built for low cost, compact size, and lightweight, they're probably not close to optimized. These have a great deal more room for improvement, and it justifies or makes sense that we might get these kinds of results. Now, typically at this point in the video, what I would do is say, hey, thanks for watching. Please subscribe. Give us a comment if you have any questions or any feedback that you'd like to give. I read all the comments and I try to address as many questions as you present. However, if you've watched our most recent live stream, we made the announcement that we're changing a little bit about our scheduling for our channel. We are now, with this video, going to begin releasing all of our videos on Saturday mornings. And we can't produce a video every single week, so we may skip a couple of Saturdays, but when we do release the videos, it will always be on a Saturday morning. And on those Saturdays, when we release a new video, we're going to be hosting a live stream at 6 p.m. Eastern Time that same Saturday. So we can address any kind of questions you have in science, engineering, technology, as well as the current video that we just released. If you've got some questions, criticisms, suggestions, anything that you want to talk about, it'll be fresh in everybody's mind. So to end this video, what I would simply say is, thank you very much for watching. Stay safe, and we'll see you tonight.